Yes friends, welcome once again to the class. Let's start our parity conservation concept. And if you want to follow this series seriously, okay, today's class you will understand only if you have watched the previous lectures. Okay, in the description of this video there is a link. Okay, that link will make you go through the playlist of nuclear and particle physics. Okay, so if you haven't watched the previous lectures, then certainly you should go to the link in the description and watch from the very first class. Only then you are going to understand today's class. Otherwise, it won't be difficult. It won't be very easy for you to understand everything, because in today's class some of the old class concepts are being used. Okay, will be used after some time. You will realize this. Okay, so you should certainly watch the previous lectures before coming to this particular class. So let's start with parity conservation. Okay, and let's see what is this parity conservation all about. Okay, so nuclear states are characterized by definite parity, which may be different for different states of the same nucleus. Now you know this very well, that the way we have atomic configuration, electronic configuration, you have learned about electronic configuration in your lower classes, right? That how the electrons are filled in the atomic shells. Similarly, in a similar fashion, nucleons are filled in nuclear shells. The way electrons are filled in atomic shells, in a similar fashion, nucleons, okay, the way electrons are filled in atomic shells, similarly nucleons are filled up in nuclear shells. Okay, so how nucleons are filled up in the nuclear shells, that particular thing we are going to learn from the next class onwards, when we will learn about uh, what we can say, uh, shell model, nuclear shell model. Okay, when we will learn nuclear shell model, it will become even more clearer to you that how nucleons are filled in various nuclear shells. Okay, so that is the thing, but for the time being we are learning about parity conservation. So nuclear state means the same nucleus. Okay, suppose we have 2He4 nucleus. Okay, suppose we have 2He4 nucleus. But in this 2He4 nucleus, the four nucleons which we have with us, they might be filled in a different manner. Okay, they might be filled in different manner. The nucleus might be in excited state, the nucleus might be in ground state. Okay, so if the nucleus is in the lowest natural state, okay, lowest possible state, if the nucleus is in lowest possible state, then it is called ground state. Okay, and if it is in excited state, then what happens? The nucleons might be excited to some uh, nuclear shell, to some particular nuclear shell. Okay, so it will become even more clearer to you after you study the nuclear shell model. Okay, now parity conservation. Nuclear states are characterized by definite parity. Okay, each and every nuclear state is characterized by definite parity, and this parity may be different for different state of the same nucleus. Okay, so for some particular nuclear state, the parity might be different. For excited state, the parity might be different. For ground state, the parity might be different. Okay, so for different state of the same nucleus, the parity is different. Parity is conserved in interaction between nucleons. Okay, whenever there is interaction between the constituent nucleons, whenever there is interaction between constituent nucleons of the nucleus, whenever there is interaction between constituent nucleons of the nucleus, parity is conserved in such interactions between the nucleons. Okay, so the thing is that parity of an isolated system remains conserved. Now what does it mean by isolated system? Isolated system is such a system, an isolated system is such a system in which the there is no interaction between the rest of the world. Okay, the nucleus is in itself isolated. Okay, It is a completely hypothetical concept. Okay, in reality we cannot isolate anything from the world. Okay, some interaction will happen, no matter however you, no matter in no matter how much you try to isolate a particular thing in the universe, still there will be interaction. Okay, so it is a hypothetical concept that we are isolating something. But if such a isolated nucleus, if it ever existed, if it ever exists, okay, or if suppose it exists, then the parity of such an isolated system, for example a single nucleus which is isolated, okay, so parity of an isolated system remains conserved. This is the thing which you must remember. Now this is one particular nucleus which whose symbol, the symbol of this particular nucleus is X. The symbol of this particular nucleus is X. Z is the atomic number of this particular nucleus. A is the atomic mass number of this particular nucleus, and it is in its excited state. Star means excited state. Okay, star represents excited state. Now this particular excited state, now this is a completely isolated system. Suppose this is an isolated system. Okay, then what happens? Suppose this particular nucleus in the excited state had even parity. Okay, and after that from the excited state the nucleons come back to the ground state, and after the nucleons jump from the excited state to the ground state, the nucleus comes to the ground state. Okay, and gamma rays are emitted in this particular process. So suppose we take an example that suppose this nucleus had even parity. Suppose I am saying suppose. Okay, suppose it is just an assumption. It is just an assumption that this particular nucleus had even parity when in excited state, and the system is isolated, right? So the system emitted a gamma ray, the nucleus emitted a gamma ray and came back from excited state to ground state. Now in this excited state the nucleus had even parity, and in this ground state the parity might be different. But if we take the parity of this entire system, if we consider that this was a system and after that the emission of gamma ray, this particular thing is a system, it is a complete system, then the parity will be conserved for this system. This particular system, that is the system consisting of this nucleus and gamma ray, this particular system will also have even parity. Okay, this particular system will also have even parity, right? So it had even parity before, and after getting decomposed means after emitting the gamma ray, I am saying, even after that the system will have even parity only. Okay, so because the system is isolated, that's why parity will be conserved. That is, this particular thing had even parity, and after getting decomposed, after gamma ray decay, the system again had even parity when we took the parity of gamma ray and this nucleus together. Okay, please remember this thing that we are talking about the entire system. Okay, if you take the individually parity of this and individually parity of this, then parity will not be conserved. Okay, we are talking about system. If you look at this nucleus, and if you look at this particular nucleus and this gamma ray individually, if you look at all of them individually, then the parity will not be conserved. If you look at all of them individually, then the parity will not be conserved. But if you consider both these things to be part of the same system, then the parity is going to be conserved. If this had even parity, then this will also have even parity because the system is isolated. That's why. Okay, the way energy is conserved in an isolated system, the way energy is conserved, the way energy is conserved in an isolated system, similarly parity is also conserved in an isolated system. But you must remember this thing, that in a weak interaction, okay, in a weak interaction, for example beta decay, in a weak interaction like beta decay, parity conservation is violated. You must remember this thing. Ah, actually my throat is in a bad condition today. So in weak interaction, for example beta decay is a weak interaction. So in these type of interactions which are weak in nature, what is a weak interaction we are going to learn in the upcoming classes. Don't worry about that, okay. I don't know what is weak interaction, so I didn't understand anything. Don't think like that, okay. We are going to learn about weak interaction in the upcoming classes. What does it mean by weak interaction and all those things we are going to learn in the upcoming classes, okay. But for the time being, just remember, that in weak interaction, for example beta decay is a weak interaction. So in such weak interactions, parity conservation is violated, okay. Parity conservation is violated in such weak interactions such as beta decay, okay. In weak interactions such as beta decay, parity conservation is violated, okay. So this fact you must remember for the time being as it is, without going into the proof of it. We will go into the proof of it in the upcoming classes, okay. So parity conservation is violated in weak interactions such as beta decay. As my throat is in bad condition, I am stopping the class over here.